in this problem, we have a pipe in a lake and it's drawing water out of the lake. Now, we're told that the height of this lake above the pipe is 3.5 meters, and we want to figure out exactly what velocity or what speed the water is going into the pipe at. Now, given some basic knowledge here. So, point 1, point 2, let's write down our knowns. We have pressure at point 1 is going to be atmospheric pressure because this is open to the air. That's 1 atmosphere, or 1.01 times 10 to the 5 pascals. Now, velocity at this point, and I'm picking pressure, velocity, and height because we're going to use Bernoulli's equation. Now, velocity at this point, with a large surface area like a lake or a huge vat, the velocity that the water is going down is basically negligible. The amount of water going through this pipe compared to the total amount of water in the lake is so small, and the area of that lake is so big that the speed that it's going down is negligible. So we can say that V1 is 0 meters per second. And the last thing we have is Y1. We're going to define Y1 at 3.5 meters. And then Y2 would be at 0. So we have Y1 equals 3.5 meters. So again, for 2, we have pressure 2, unknown. Velocity 2, unknown. And the height of 2 is 0 meters. So we're going to use Bernoulli's equation. Pressure 1 plus 1/2 rho V1 squared plus rho G Y1. So, in a liquid, this is a constant always, in a flowing liquid. So, if the speed picks up, the pressure is going to go down. Or if you go deeper into the liquid, then you're going to get higher pressure due to the depth of the liquid, so this pressure will go down. It's always in balance. This is always equal to a constant. That's why we can say this point is equal to this point for these values. So P2 plus 1/2 rho V2 squared plus rho G Y2. Okay, so let's plug in the easy ones first. Whatever is equal to 0, right? So velocity 1 is 0, so this whole term is 0. Y1 or Y2 is 0, so this whole term is 0. So we have, let's rewrite this, we have pressure 1 plus rho G Y1 equals pressure 2 plus 1/2 rho V2 squared. Okay, let's solve for V2. Well, just this term. So we'll have 1/2 rho V2 squared equal to pressure 1 plus rho G Y1 minus P2. Now, since this is a constant value, and we want V2 to be maximum, so we want our velocity to be maximum, that's what it states in the question, this term has to become a maximum. Okay? Now, P2 is going to be subtracted off the total. So the higher P2 is, the lower the velocity is. So since P2 can only be a positive value from 0 above, we want it to be the lowest it can be, 0 for a maximum. So P2, 0 for Vmax. Okay? So we're going to make that 0, and this becomes V2 max. So we have rho over 2, I'll write it as, times V2 max squared equals pressure 1 plus rho G Y1. Okay, So now, simplify, I'm going to multiply 2 over rho over here, so we have V2 max squared equals multiplied by 2, P1 divided by my rho, plus 2 rho G Y1 over rho. So I just multiplied by 2 and divided by rho. So I take the square root of both sides, get rid of this squared, so I get V2 maximum is equal to 2 P1 over rho plus these rows cancel, giving me 2G Y1 square root. So let's toss in the numbers here. So we have square root 2, pressure 1 is 1.01 times 10 to the 5 pascals. Divided by rho. Rho is just for water, which is 1.000 times 10 to the 3 kilograms per cubic meter. That's our constant for rho of water, and that's 3 significant digits, so 1,000 kilograms per meter cubed, plus 2 G of 9.8 meters per second squared, times Y1 of 3.5 meters. That's all under the square root sign. So if we plug that into our calculator, we get a V2 max, and rounding to 2 significant digits, because that's what we're given here, 3.5, is 16 meters per second. Final answer.